testing hypothesis about the single population parameter. So when we test the population, I mean the hypothesis here, first thing we want to know is when the beta is a small number or even it's a big number, we don't know the real the population beta, right? So what we can observe is that this sample beta number. So we got a number. So what we are doubt or wondering is this number is just come from the sample because of random sampling. That's why it's happened to be a certain number by chance, or actually this is a zero. So one over my factor doesn't have any effect on my dependent variable. So beta should be zero, but since I'm collecting sample, which means there will be a lot of the error terms comes in. So that's why I got a beta hat. So we want to know, okay, I calculate the beta hat and I got some number, but I want to know this number is just happened by chance, or I want to know actually my factor has some kind of effect on my dependent variable. So that's why our null hypothesis is beta j is a 0, which means it doesn't have the factor effect. So this is the meaning. There is no effect on the xj on y. So we want to know xj actually has an effect on the y. Then we can assume, okay, what we get like a beta hat is some number, it's a random number, but depends on the sampling. You can have a different number, but still we can estimate, we can talk about the confidence interval and so on. But however, if we find out actual population coefficient is a 0, but we got a beta hat certain number only because of the like a sampling error, then that's a meaningless talk about what is the beta j or beta j hat, right? So that's our hypothesis testing. Actually, xj actually has an effect on the y or not. So 0 means it doesn't have any effect, or because we will get some number, we will not get a 0 exactly. We will get some number, but that some number can be just number by chance because we just sample, right? So we want to figure it out. We cannot make a decision. I mean, we cannot just decide it has an effect or not. It's by the size of number, because the sum factor has a obvious effect but very small effect, right? It's clear they all have an effect, but very tiny effect. Then your beta will be small. So you cannot tell the big number or small number is how strong their effect on the y. That doesn't tell you is this a statistically significant effect on the y or not. That cannot be determined by the size of number. That's why we have to have a hypothesis testing. So t statistics or t ratio will be calculated by the beta hat divided by standard error of beta hat. That will be the t, and then if this t is greater than our critical t, then we reject our null hypothesis, and if this t is smaller than our critical t, then we cannot reject null hypothesis. T-testing against the one side of the alternatives is greater than 0 or not. So you can set it up like a null hypothesis, one side, one tail. Probably you have learned the one tail testing or two tail testing. So it's greater than 0 or not. So reject the null hypothesis in favor of the alternative hypothesis if the estimate coefficient is too large, right? larger than the critical value, we will find out the t. This is a t distribution, and then our t, this is a critical t. And our t for here, then you can tell the probability of getting this t by chance is smaller than 5%. So we reject our null hypothesis. If our t calculation happen to be here, then the probability to get this t, so null hypothesis, the hypothesis testing is always like that. If H null hypothesis is true, what is the probability getting our current t, right? Right? If this is a greater than is smaller than 0.5, which is 5%, then under the 5% confidence, we can say, yeah, if this is true, it's almost impossible to get our current t statistics, which means H0 is not true, so we can reject. However, if this probability is greater than 0.5%, which means even though null hypothesis is true, still we have a large enough probability to get our current t statistics, which means I'm not sure H0 is not true. Maybe it's true or not. So that's why we take a look at it, calculating our t statistic and compare to the critical t that's tied to this probability, and then compare these two numbers, and then we're gonna make a decision is reject or not. So this is one example, wage 1. This is I think this sample we used in the previous chapter. So to make it more favorable for the normality assumption, so we take a log here, okay, and then we do the regression. So we find out all these numbers, right? This is our regression model, and then these parentheses numbers are our standard error. So you can get a standard error from the Excel or from the other number. So total number of the data is 526, R square is 0.316. So you will get how many number we estimate is 1, 2, 3, 4 number estimated, right? So you will calculate the degree of freedom, and then depends on the percentage, you can find out the t value, critical t value, and then we can calculate our t value. Standard error of this b beta j will be our t score. So t score versus the critical t value, then we can tell we can reject null hypothesis or we cannot reject null hypothesis. So talk about the experience in the previous section. Right here, we talk about this experience. So that's why t statistics is 0.0041 divided by 0.0017. So you calculate the t value for our current experience is 2.41, and then degree of freedom is n, which is 526, and this is minus k plus 1. So k is number of factor. Actually, how many parameter we estimate using this model. 1, 2, 3, 4. So actually we estimated beta 0, beta 1, beta 2, beta 3. So we use three factors, dependent variable, but since there is an intercept, so actually we have a 4 parameters. We estimate 4 parameters. That's why you have to subtract the 4, which is minus 3 and minus 1. So these 3 is the factors, this 1 is for the intercept, and then you can get this is our degree of freedom, and then you can find the critical t. Okay, this is the one of the t table. You can find a lot of different table, but this one tells you this is 50%, 75%, 80%, 90%, 95%, and so on, right? And then one tail or two tail case, and then degree of freedom. So our degree of freedom is like 500. So right, you can use 1000, right? Because the number is not that change that a lot, right? So you can use like 1000, and then our case is 95% case is one tail, right? This one, and then degree of freedom is about 1000, right? So you can tell it's a critical T will be the 1.646. Right? As you can see here, the 5% case is 1.645. So our T is a 2.41. So again, that means this one is if this is a T table, right? This critical T is 1.645. Then this probability will be 5%. That's why in the table I look for the 95 case, 95%. But our T is greater than this one, so our T located here, right? Which means the probability to getting our data, our number, our model, if null hypothesis is true, what is the probability we can get that our result? That probability will be way smaller than 5%. So that's why we can reject the null hypothesis, which means our beta for this experience will not be 0, which means the experience has a significantly statistically greater than 0 effect. Okay, so effect on the experience on the hourly wage is statistically greater than 0, which means they have a significant effect. So here the significant effect does not mean it has a huge impact. Okay, so it's not talking about how strong the effect is, but we can tell statistically it has a meaningful effect. Yeah, if you use a 99% or 1% error significant level, the critical point is 2.3. Still, is 2.4 is greater than 2.3. So you can tell with a 1% significance level, still the beta for the experience should be greater than 0.